Okay, in this section, we're going to talk about tangent lines and the derivative of a curve at a certain point. And we've talked about this a little bit before and kind of gotten some of the geometric interpretation. Let's draw another picture and kind of talk about this again. So if I've got a curve and I'm trying to find the slope of the tangent line, what we're going to do is we're going to have a couple different points on the curve, and we're going to bring them close together and see what happens to the slope between those 2 points. So if I have a point at A, this is going to be at f of A, so this point is at A comma f of A, and I've got another point over here, and I've got a tangent line, or a secant line, between them right now. But then if I slide this point along the curve, so it gets closer and closer to the first point that we have, that curve, that slope is going to get closer and closer to the slope of the curve at this specific point. So it's going to get closer and closer to the curve's actual slope at that instantaneous point A. We do this with a difference quotient, and I'm going to write that here. So how we're going to do that is we're going to think about this red point as being at, this is at A plus H away, and so this is at A plus H comma f of A plus H, and so the slope between the blue point and the red point is going to be f of A plus H minus f of A, the change in the y values, divided by the change in the x values, which is going to be A plus H minus A. So that slope of that specific secant line, given this set H, is going to be f of A plus H minus f of A over H, because the A's are going to cancel, plus A and minus A. Okay, to find the slope of the green line, I'm going to take the limit of this difference quotient as H gets closer and closer to 0. That is, that the red point gets closer and closer to the blue point. So that's our definition of the derivative. The derivative of a function f at a point x equals A is the limit as h goes close to 0 of f of A plus H minus f of A over H, and is denoted f prime at A. Okay, so let's see an example of computing this, and then we'll do some geometric interpretation of this stuff too. Okay, so let's do an example. F prime at 3 is computed as follows. For f of x equal to, let's go x squared plus x. So we want the limit as h goes to 0 of f of h plus 3 minus f of 3 divided by h, right? So that's going to be h plus 3 squared plus h plus 3 minus 3 squared plus 3 all over h. And we haven't taken a limit yet, so we still have to keep that there. Algebraically, this turns into h squared plus, keep this limit here, h squared plus 6h plus 9 plus h plus 3 minus 9 minus 3 all over h. That 9 and that 3 cancel, and I've got an h in a bunch of these terms. So that's the limit as h goes to 0. If I cancel out h, I get an h plus a 6 plus 1. So that will be 7. So that's the derivative of f at 3. This is f prime at 3. Okay. So geometrically, what that means is the slope is positive and it's fairly steep at the point 3. Let's look at a graph and see a couple different geometric ideas with the derivative here. Maybe I start out fairly flat, I increase, I go basically vertical, I come slow down again. Maybe I hit a maximum in here somewhere, I hit a minimum in here somewhere. Maybe there's like a cusp here, so it comes up to a point and then drops back down. And then maybe I've got a jump or something in my graph. Okay. So we get to break this up into different bits. At this point, f prime is equal to infinity. I've got a vertical tangent line. The slope of the graph is straight up and down. The slope is infinity. Where it's flat here, I've got f prime is equal to 0. It's flat and I've got 0 slope. In here, I've got f prime is bigger than 0. It's a positive slope. The graph is increasing. Still increasing in here. F prime is still bigger than 0. At this maximum, wherever this maximum is, f prime is equal to 0 because the slope's flat there. It's not getting higher or getting lower at that point, so it's a maximum. At a minimum, I also have f prime is equal to 0. Here I've got f prime is less than 0. Here, f prime is undefined. I can't tell you what the slope is because it could be anything from positive stuff to negative stuff, right? There's no specific slope there. Any line I draw through here could be kind of thought of as a tangent line. So it's undefined there, and it's also undefined here, right? Otherwise, I've got f prime is less than 0 there, f prime is bigger than 0 there. So graphically, you can kind of see what the tangent lines are doing, and that tells you what the slope is doing, which tells you if the derivative is positive, negative, 0, infinity, undefined, that kind of stuff. So that's kind of your geometric interpretation and your actual mathematical definition of what a derivative is at a certain point. In the next video, we'll do some examples of actually finding a tangent line and a couple more of computing a derivative.